Momentum of mechanical system and the momentum change theorem. Article 10.8 of the book Mechanical Systems, Calculations of the Marine Facilities. Momentum change theorem. A little bit about the theory. This is one of the widely used theorems in the dynamics and mechanics when we're considering the motion of the mechanical point that is a concentrated load, or the motion of the mechanical system consisting of the loads, or just the continuous mechanical bodies, etc. Momentum change theorem usually we consider in three forms. The first and the second forms are differential, and the third form is integral. Integral. So let's consider a little bit about the theoretical concepts, and after that we will do some exercises. What is the momentum? Momentum is the amount of the mechanical motion. We consider momentum as or the mechanical system or the mechanical body consisting of the indefinite one definition consisted of the discrete parts, the discrete concentrated loads. In this case, the momentum we consider as the total momentum of the mechanical system or of the mechanical body consisting of the discrete parts. We consider as a total of the momentums of the single parts, of all single parts considering together. And the momentum of the case single part equal to mass of the part multiplied by the velocity of the definite one part of the mechanical system. That is could be the parts of mechanical system or just the mechanical points as the concentrated loads. And we have the vector magnitude in the product vector magnitude of the velocity of the definite one part of the mechanical body, and that is why the momentum of this mechanical part is equal as well, is the vector magnitude as well, and the momentum of the integral mechanical system or mechanical body as well as the vector magnitude, momentum of the mechanical system of the solid body, independence on its mass. We can find as we'll find the product of the mass of the mechanical system by the velocity of the center of the mass of the mechanical system or the discrete body consisting of the separate concentrated loads. This is the mass definition of the mechanical system or the body, and this is the velocity of the center of the mass of this mechanical body. So in the first form differential, the momentum change theorem, we can define as the time derivative of the momentum of the mechanical system is equal to the sum of the all external forces, the vector main vector of the external forces. So this is a vector of external forces acting on each of all discrete parts that belong, which belong to the mechanical system or discrete, or the body consisting of discrete elements of these external forces, the total acting on the system. This is a vector magnitude. And for each element, we have an external force. We have to consider this is the force is a vector magnitude. This corresponds to the concept of the momentum as a vector magnitude. And we have the derivative of the momentum equal to the force acting on the mechanical body. The change of the momentum, that is the amount of mechanical motion or the momentum, which is more correct to say the momentum, the amount of mechanical motion of the case element of the mechanical system is a derivative. So a general approach, this consists of the total of the external forces and the internal forces acting on this definite one element of mechanical body. But we have to know that if it is internal forces, it is the internal forces. Forces acting in between the elements of the mechanical system or the body consisting of the discrete parts. And when we consider this in general, usually this interaction in between in each couple of the mechanical system, between the elements of the mechanical system, the discrete elements of the mechanical system, they are compensated in pairs. Compensated, so it only remains external force action of the mechanical system. If we consider the integral mechanical system, but some choice could be of the consideration of the separate parts of the mechanical system. The change of momentum is determined. So here we have about the same formula, but just the total, and with the force we have as well the total. This is for case elemental mechanical system formula, but this is for definition of the total mechanical system. The total of all forces, a vector total. This is a vector total of all momentums. That is the amounts of the mechanical motions of the separate parts of the elements of the mechanical system. Because the sum of inertial forces acting on each element from the other elements is equal to 0. That's why we can reduce this with not the second summand. Only the first summand remains in the total. And besides, we can define the projections on the coordinate axis if the momentum is the vector magnitude, then yes, the components in projection on the axis, on the abscissa axis, the derivative of the momentum by time equal to forces action in the projection on abscissa axis, the same on ordinate axis, and the same on the applicate axis, the derivative of the first derivative by time of the momentum. Momentum is the amount of mechanical motion component on the applicate axis equal to projection of all forces on the applicate axis. External forces is external. I is internal. E is external forces. This is a first form of the first differential form of definition of the momentum change theorem. That is the change of the momentum equals to the action of the forces. This is the second form of the momentum change theorem. This is differential form is the first one. We had the first one theorem, the derivative of the momentum amount of the motion equal to the product of the mass of the definite one element of the mechanical system. This is total of all elements by the velocity of this element mechanical system. So this is momentum, the derivative of the momentum equal to the action forces. As we have here mass inside the product when defining the momentum product of the mass by the velocity, then the mass usually not depend on time, so the velocity depends. So the first derivative of velocity by time is the acceleration. We will have the acceleration on the left side. Product of the mass by acceleration. This is the force. In accordance with the second law of the mechanics of Isaac Newton, and this is to be multiplied. We can do different, very simple mathematical transform. Just remove the denominator from the left side to the right as a factor, and we will have on the left the differential, the increment of the momentum. On the right, we will have the total force multiplied by the increment of time. So the change of the momentum equal to the action of the force for the same time period as the momentum change we consider. So, and we can define the, instead of that, we can define the impulse. This is the product of the force by the increment of time is the increment of the impulse. Impulse is about this very close concept to the momentum. Momentum is characteristic of the motion mechanical body. The impulse is characteristic of action of the force of the mechanical body per definite period of time. In this definite one differential form, we have the period time equal to increment of time, very small magnitude. For this is as well the second differential form in projection coordinate axis, the momentum change theorem. Second form, the same differential, the previous one. The previous one was the derivative of the momentum equal to action of total of the action forces. In projections, we have the last one, three formulas. The last three formulas here, and in projections axis. So here we have in projection axis the increments of the momentum equal to increments of the impulse. The force, if we consider within the small period of time, the impulse is the constant magnitude. So the same, but all the increment of the time it's during the whole time period. So increment of the momentum equal to increment of the impulse of the external forces. The projection of this axis is the same as well, and the total of all increments of the impulses action of the forces on all the discrete elements of the mechanical body. This can be done as well, not for the continuous mechanical body, with not the total, but with the integral operation for the continuous mechanical body. But we usually consider the practical needs the discrete set of the mechanical elements in the mechanical system. So it could be the points, mechanical points at the concentrated load. So it could be discrete elements of the mechanical other discrete elements of the mechanical system. So this is projection ordinate axis as well of the momentum of the impulse. And this is the projection applied axis the same. And the next form of the momentum change theorem, the form number 3, we say the integral form. Momentum change theorem, the integral for definite, we can take this one, the differential form is the differential equal to the forces section. But in this one, for example, that the increment of the momentum equal to the increment of the impulse action during the very small period of time equal to the increment of time. So this is the integral of this function of the first and the last one equations. And this follows from that, and the projections on the coordinate axis, the equality of the system momentum change equal that the differences of the momentum. So the mechanical system at the end and the beginning of the considered time interval from 0 to t is a momentum for initial time interval. This is as well in projections on the axis of subsys ordinate and applicata equal to the impulse of the external forces acting on the mechanical system during this time interval from 0 to t. This is the form of the momentum change theorem. So we have usually two differential forms. First, the derivative of the momentum equal to the magnitude of the action of the forces acting on external forces acting on mechanical system. Second, the increment of the momentum equal to the increment of impulse for the time of the action of the external forces. And the third is that is the difference of momentums for the definite time period equal to the impulse magnitude for the same of the action of the forces as the force multiplied by time for the constant force, if not changed the force for the time period. It is the impulse for definite time. For the variable force, this is integral dependence of the force by time integral for definite time period. And we have the consequences of the momentum change theorem. The first consequence is the main vector of external forces of the system is equal to 0. That is the external force equal to 0. Then the amount of mechanical motion of the system, that is the momentum, is of the constant magnitude and direction. The momentum is constant. If the projection of the second consequence of the momentum change theorem, if the projection of the main vector of all external forces of system onto the another coordinate axis is equal to 0 of one or another coordinate system coordinate axis is equal to 0 from the among the projections of the forces. So we have the projections on axis of the external forces. So yeah, this have to be as well the sign of the total. Sign of the total have it here. Yeah, I'm sorry, just please correct this. Then the projection of the momentum of the system on axis is constant. That is understandable. And we have the exercise. Let's consider the mechanical system shown on the figure 10.8.1a. We have three concentrated masses, the three concentrated loads in the points A, B, C. This is equilateral triangle with the side equal to A side of this equilateral triangle. And we had two velocities assigned of the points A and the point D. So the velocity is of the same magnitude, but on the other direction. So this VA equal to VD, but directed to the one upward, another one downward. And we can associate the coordinate system. This is a flat motion because all motions vectors are in the same plane. This is the plane of the draw on figure 10.8.1. This is a plane motion in the coordinate system x, a, y. Y is the origin of the coordinate system, the reference point actually. So the question is, what is the momentum of this mechanical system? This is weightless rods, rods, this rods, wedgeless. So the masses we have here. The amount of mechanical motion of the specified system is equal to or the mass of all mechanical system multiplied by the velocity of the center of the mass. This is vector magnitude. This is amount of mechanical motion. That is momentum of this mechanical system. And on the other hand, this equals to the masses, total of the masses of each of the loads A, B, D, three loads. We have point C, but the point C is the center of the gravity, center gravity of this center mass of this mechanical system. So we can use the letter D as so the vertex of this triangle equilateral. Angular velocity mechanical system we can find easy because this is a plane motion, and the instantaneous center of velocity is here in the point P, as we have two velocities, one directed upward, another one downward, parallel to the coordinate axis. Then we just can connect them, the ends of the vectors, by the straight line and in the intersection. Exactly, that's understandable. That is x, b, and the center of the instantaneous center velocity p. The coordinate is y is 0, which is on the abscissa axis, which passes through the points A and D. And this is in the middle. So if we have the A, the size of this, each of the sides of this equilateral triangle, that is xb is equal to A divided by 2. So we can just divide a velocity, for example, the velocity of the point A divided by the AP. AP is A divided by 2. So A in denominator and the 2 comes to numerator. The velocity of the point B, the direction of which is shown on the diagram, the right one. So this is instantaneous center velocity. That is the point B velocity directed by the perpendicular to the radius from the instantaneous center of the velocity to the point B. So the velocity of the point B direction, the rightward direction, this rotates the clockwise. The rightward direction velocity, instantaneous velocity of the point B equals in the magnitude as the omega. Omega is the angular velocity of instantaneous angular velocity multiplied by the radius BP. The instantaneous mechanical system velocity angular is 2 by VA, or we can say just a V, as VA have the same as a V. We can divide by the 2 by V divided by A. This is the angular velocity multiplied by the A multiplied by square root 3 divided by 2. What is that? This is on the left side of this unilateral triangle. If we divide into two equal symmetric triangles, right angle 90 degrees. This is hypotenuse equal to A assigned size of the unilateral triangle, and this is each of the angles of the unilateral triangle is 60 degrees. That all angles together, internal angles, all angles together are 180 degrees. So each of them is 60 degrees. So the half is 30 degrees. So we can multiply all this hypotenuse size by the cosine of the angle of this half angle of the vertex B is 30 degrees. Half is all angle is 60 degrees. Is half is 30 degrees. Cosine of 30 degrees is square root of 3 divided by 2. So we can just reduce for these two factors to the denominators, 2 by 2. So we have that velocity of the point B is equal to the velocity of the point A or point D, the same velocities, directed in the other directions parallel, multiplied by square root of 3. Next, as well, we have to find the position of the center of the mass of mechanical system. We got the velocity. I don't know why. Okay, this is okay. The position of the center of the mass of the mechanical system by the abscissa axis is understandable because this unilateral triangle is symmetric, of symmetric shape. This is x-axis. So this is the half of one of the sides, that is A divided by 2. But we can find that considering the static moments of relative coordinate axis, because we have to find in this first one approach of the abscissa. So the static moment relative coordinate of the masses of each of the points multiplied by the abscissas of each point relative to the coordinate axis. And in the denominator, we have the total of all masses of these points in the mechanical system. So we'll have 3 by m, and in the numerator, we have A divided by 2. So the first was one point A load. The abscissa is 0 because it coincides with the reference point. So remains only the second and sum, and the point B is the abscissa A divided by 2 by m. And the point D abscissa is A by m. So we have together the abscissa of the center of the mass of this mechanical system we call A divided by 2. As well, we can find for the YC, the ordinata. This is total, so the static moments of all masses relative abscissa axis, because we have to find the ordinata of the center of the mass, and this is the same total of the masses of the mechanical system. So if we have 2 loads on the abscissa axis, so ordinatas of the points A and D equal to 0, only one remains. One is located at the proximity from P to B. This is YB. The YB is A, the side of the unilateral triangle. That is A multiplied by square root of 3 divided by 2. This is together the cosine of the angle of the 30 degrees by the vertex half of the angle. And the next multiplied by the m of this point B and divided by 3m. 3m is a total 3m's in this mechanical system. We have A multiplied by square root of 3 divided by the magnitude of velocity we see of the center of the mass. So we did find the coordinates of the center of the mass of the mechanical system located here. This is understandable and obvious because for the symmetric unilateral triangle, we know for sure that the location of the center of the mass, if we have the vertices the same loads of the mass m, equal masses, the center of the mass of this mechanical system is in the intersection of any 2 bisectors of the vertices, or all 3 bisectors, or intersection of any 2 medians dividing the segments dividing the opposite side by half to half from this medians, intersection of 2 medians. The same gives us the location of the center of the area, or center of the mass of this mechanical system. So, but anyway, formally we did, and we found that the abscissa and ordinata of the center of the mechanical system, a magnitude velocity of the center of the mass equal to the distance yc, the ordinate of the point of the velocity yc we got here, this A multiplied by square root 3 divided by 6, and multiplied by the instantaneous angular velocity we got previously here, 2v divided by A. This is instantaneous velocity, and we can find that this velocity of this point C, the center of the mass of the mechanical system, equals to directed to the right. Exactly, this is understandable because this is instantaneous center of the velocity, this angular velocity. This is a radius, and perpendicular to the radius we have direction of the velocity of the point C equals to the v is assigned the velocity of the point A upward or the point D downward, and multiplied by square root of 3 divided by 3. This is due to the definition of the ordinata CP. CP ordinata of the center of the mass of the mechanical system, YC. Okay. The magnitude of momentum actually we can find as well by the product of the mass of the mechanical system. Total mass is 3m, 1m, 2m, 3m, multiplied by v velocity of the center of the this v multiplied by square root of 3 divided by 3 is the velocity of the center of the mass of the mechanical system. That is the momentum of this mechanical system. What we have to find for this definite one issue. Okay, the next one issue, the very simple issue for the momentum change theorem. We have to find the velocity of the load which moves from the state of rest to downward, and the velocity of the load and dependence on time. So let's consider this load located on the inclined surface. We have the factor of the friction as well. We have, and we have to consider the change of the momentum of this load. The momentum we subtract from, we can subtract from this the momentum at the end of the motion assumed at assumed time t, and the momentum of the initial moment of the motion of the this load on the inclined surface with the friction. But we can consider this in the projections on the abscissa axis. But the momentum at the initial time moment, because the load was in the state of the rest, so it was equal to 0. So we have the momentum only by the action of the forces in the projections on abscissa axis. All forces acting on the this definite one load moving by the inclined surface. And we have two forces acting in projection on abscissa axis. On abscissa, we have the force of the wedge, I mean the vertical, no vertical component, but the projection of the wedge by the component parallel to abscissa axis. So this is the P, the wedge of this load directed downward, multiplied by sine alpha, sine of the angle of the inclination of the surface, the same angle between the normal to the surface and the vertical direction of the wedge force acting on the load. And we can subtract the friction force, the same as the normal force. Normal force is the wedge multiplied by cosine alpha. This is projection of the wedge force onto the normal direction. Normal direction is parallel to the ordinate axis. Normal force reaction multiplied by the factor of the friction. After the equation, the equation, the right side of the impulse of the force during t period of time, this has to be equal due to the momentum change theorem to the momentum in the definite time moment. Momentum of the load in the motion equal to mass of the load multiplied by the velocity of the motion. This is exactly the projection on the horizon, on the abscissa axis. And we have equality of that, the wedge equal to mass multiplied by the gravity acceleration, the wedge as well multiplied mass by gravity acceleration, sine alpha time t. So after a very simple mathematical transform, we find that the velocity magnitude at time moment equal to t is sine alpha minus cosine alpha multiplied by the factor of the friction, the friction of the dry friction, multiplied out of the brackets by the acceleration of gravity, 9.81 meter per square second, multiplied by time. This is answer for the question, what will be the velocity of this load, definitely one load P. Even with not the definition, we don't need to set the mass. We just need only to set the angle alpha and the factor of the friction and the time moment. Because we, when we do the simplification of this equation, we reduce the common factor mass from all of the summands on the left and the right sides of the equation. Okay. Oh, next exercise. Exercise number 3. We have the wheel and platform number 1 moving with the velocity v1 along the horizontal surface. It could be the railway platform or just only the paved road platform. It's not so much important. This is definitely one consideration. We neglect the friction, the rolling friction. This platform moves, and related to this platform, this number 2, small car moves to the right with a relative velocity relative to the platform of v2 is the second one element of mechanical system. The first one platform, the next one car, and the velocity of the car is equal to v2 relative to the platform. So Let's consider the question we have assigned. What is after the collision, after the inelastic collision of this car with this one stop, with the part of the moving platform, rolling wheel and platform. After the inelastic collision, when this car will impact this stop and will next go together with the platform with the same velocity. This will be the inelastic collision, which will be the common velocity of the system consisting of this platform and the car on the platform after the inelastic collision of the car with the stop on the platform. So we can consider the integral form of the momentum change theorem, that the difference of the momentum is equal to impulses of the external forces, equal to the action of the external forces. And the difference of momentum mechanical system. So this momentum mechanical system consists of two momentums: momentum of the platform, momentum of the motion of the car, together with the platform and related to the platform. So this car consists two momentums: momentum of the car, because this is formally the complex motion consisting of the transfer motion of the system of the coordinate. System of coordinate for the platform motion relative velocity definition is the system associated with the platform moved together with the platform. Okay, so, but we do not have the external forces acting on the mechanical system or on its element from the outside in projection on the abscissa axis, because the force is only weights of the car, weight of the platform directed downward, and the platform in the car are moving on the by the horizontal surface, and so we do not have the velocities of car or the platform, the company directed by the horizontal axis abscissa. So, since after we have equal to zero, if after the collision, inelastic collision of this car with a stop on the platform, the momentum is the same as before the collision. So the difference of the momentums after collision equal to zero, with absence of the external forces in the horizontal components acting onto the platform and onto the car on the platform. Since after the collision, the momentum of the mechanical system is equal after the collision to masses and the definite velocity u of common velocity of two elements mechanical system of the platform and the car, the velocity u, the component velocity of these two elements together moving after the collision with the car with this stop, and this is subject to find the velocity. It is assigned to find which is the u common velocity of these two elements of mechanical system after then collision of the car to the stop of the platform. This momentum equals to initial one momentum, because if there is zero, then the qx projection momentum after collision equal to the q0x. We can remove it to the right side with another side. And before the collision, we have the motion of the platform, the mass m1 with the velocity v1, and the velocity of the car on the platform with and the momentum of the car motion on the platform with the two velocities of velocity of the platform and velocity of the relative velocity of the car relative to the platform. And if these momentums are equal to qx and q0x equals, then we have the equation. The right sides we equated to each other. Next, after very simple mathematical transform, we can find what is equal the velocity of the system of the platform and the car moving after the inelastic collision of the car moving here with the velocity q to r, and when it stops relative the platform by the collision of with the stop of the platform. Okay. Oh, questions and comments. The momentum of mechanical system or of a solid body consisting of parts of mass elements is equal to the sum of momentum of all elements of the system of all elements of the mechanical. Yeah, that is, we can consider separately the discrete elements of the mechanical system or discrete elements of the mechanical body, discrete parts, as the concentrated loads of this the mechanical points, the concentrated loads of the mechanical points which are included in the mechanical body on the mechanical system. And we consider the motion of these points separately. And the momentum of the mechanical system on the one hand equals the mass of all mechanical system multiplied by the velocity of the motion of the center of the mechanical system, or this body consisting of discrete elements, the same as for the continuous body. In practical needs, usually we consider the discrete bodies. And on the other hand, this equals to the total of the momentums of these all elements considered separate. These elements are moving in the direction of the external and the internal forces. Internal forces, forces action on each element on behalf of other elements mechanical system. Total action of all internal forces on the elements mechanical system do not change the momentum of the total mechanical system. So it can, one element mechanical system can act and change the momentum of the another element mechanical system, and as well the another change by the same magnitude the momentum of the first one element mechanical system. But they together do not, the interaction of the internal forces between the element mechanical system do not change the momentum of the total mechanical system, complex mechanical system. 10H2. The vector value of the momentum of the mechanical system is equal to the product of the mass of the system, the sum of the mass of elements of the system, or the elements of the body mass, by the vector of the center of the mass of the mechanical system, by the velocity vector of the center of the mass. Yes, it is. So this is definition. So 10A3, first form differential one momentum change theorem of a mechanical system is an equality of the time derivative of the amount of mechanical motion, that is momentum, of the system, that is of all elements, to sum of all external forces acting on the mechanical system, since the internal forces acting between the elements of the system, when they are added are reset, then they do not lead to a change of the mechanical system momentum. So the first form, that differential form, the derivative of the momentum of the mechanical system, all the first derivative by time equal to the impulses action for the definite one period of the external forces on the all elements mechanical system. External forces, they only we consider. TN8 for the second form, this is as well the differential one of the momentum change theorem of mechanical system following from the first form of this theorem. I mean that maybe all forms of the momentum change theorem follows from each other. And the second as well follows from the first one. Form differential. That is, the incremental momentum of a mechanical system, the product of total mass of all elements of the system by the increment of the common center of mass velocity vector, or the period of differential time increment, is equal to the vector of mechanical impulse of all external forces during the period of the time increment. This directly goes from the first differential definition of the momentum change theorem. Just if we will do the simple mathematical transform, if we will move the denominator from the definition of the derivative, first derivative by time of the momentum from the left side of the equation, we will remove it as the factor to the right side. We will have on the right side the impulse of the force, that is the action of the force during definite time period. In the differential form, the time period is equal to the increment of time. Very small elementary increment of time. 1085, the third form, the integral one of momentum change theorem of a mechanical system, the change of mechanical system momentum over a period of time is equal to the integral of the vector sum of mechanical impulses of all external forces acting on the system over the same period of time. If we will consider the second form of the momentum change theorem, that is the increment of the momentum, dq is the increment as a very small momentum for small period of time, equals to the product of all external forces by the increment of time, during which we consider the change of the momentum. This we can do, this two increments we can find as the subject of the integrands on the left side, the integrand for definite time moment. From an original velocity to another one velocity, we can find the change of the momentum. The that is the amount of the motion of the all elements mechanical system. And on the right, we will have the integral of the force by the time of the action of the force. This is the integral form of the momentum change theorem, which goes from previous two forms. 10.86, the amount of mechanical motion of system is constant in the magnitude and direction, provided that the main vector of the external force action mechanical system is zero. Yes, if the external force is zero, that is in the, for example, thought the integral form of the momentum change theorem under the integral in the integrand equation, the factor of the force equal to zero, then the difference of the momentum, such as the beginning or at the end of the time, considered in the integral form of the momentum change theorem, the integral of the force by the time equal to zero. 10.87, the projection of mechanical system momentum onto the another coordinate axis, onto one or another coordinate axis, is over the constant value if the projection on the axis of the main vector of the external forces action mechanical system is equal to zero. As the momentum is a vector magnitude, and if the force is vector magnitude, so all rules of math applied to the force, the same we have applied to the momentum. So if you have the projection of the forces on the axis, so the same we can do for the projections of the momentums on the axis. And if the force equal to zero in the projection definite one axis or to all the axes, then the momentum projection on the definite one axis on all axes will be equal to zero. This definite one case. 10.88, independence on the rotation of the system of amount of its mechanical motion, which depends on mass of its element and on translational motion of the system center of mass. So if we have the mechanical system as we considered in the first exercise, so we can consider the rotation as the instantaneously translational motion of all discrete elements of the mechanical system with not the rotation of the mechanical system. In this definite one case, if we can reduce the rotation of the mechanical system, as we have unilateral triangle connection of three concentrated loads and the connections are weightless. In this definite one case, we reduce the motion of this mechanical system to the instantaneously translational motion of all the vertices in which located the masses of this mechanical system, the equal masses in the mechanical system. So in this case, we reduce the rotation to the translational motion with the translational or progressive velocities, instantaneous velocities of the elements, weighted elements of the mechanical system. So we can do independently on the velocity of the rotation, angular velocity. 10.89, the amount of motion of a mechanical system under the influence of the mechanical impulses of several external forces equal to the amount of the mechanical motion under the influence of the impulse of the main vector or the external forces. Yeah, so if we will have, instead of all forces, the resultant force 1, so we will have the projections of the resultant on the coordinate axis. Then the amount of the motion, the momentum of the mechanical system, that is under the influence of the mechanical impulses of the several external forces, could be the several forces acting on the several or other discrete elements of the mechanical system. We can reduce the action of the resultant force on the mass on the center of the mass of the mechanical system. Yes, we can do that. 10.8.10, the emergence, the termination or rigid connection between the elements of the mechanical system, which is not affected by the external forces in the projectional direction of the movement, which do not lead to change of the system center of the mass velocity and its momentum. That is because the rigid connections is usually corresponded with the forces which acts between the element of the mechanical system, between the discrete element of the mechanical system. In this definite one case, we know for sure that internal forces do not lead to the change of the momentum of the mechanical system. That is why, because in this definite one case, we can consider only the motion of the mechanical system elements together. They do not lead to change of the system center of mass velocity and its momentum. Thank you.